Welcome back. In the last video, we started Galois theory after revising earlier parts of group theory, ring theory and field theory. And in the last video, I talked about group characters. And I told you that those are not important in their own right for us, but mainly when we are interested in field homomorphisms. Okay, so in particular, I wanted you to understand this theorem I proved, that if you have a group and a collection of distinct characters in a field F, then they are independent. And I also remarked that the main application of this is going to be when we talk about homomorphisms between two fields. Okay, so I want to continue this and tell you why we are going to study these characters this way and when we are going to apply this theorem. So the theorem is very important for us. You will see in the next few videos where the theorem will come in handy for us. Okay, so let me set up like that as follows. Let K and L be two fields, and let us take a collection of some finitely many field homomorphisms. So let sigma 1 through sigma n be field homomorphisms. Okay, so we are going to say that an element, so this is a definition, an important definition for us, an element A in K. Remember, each sigma is a function from K to L. So an element A in K is fixed by these given collection of homomorphisms. We say that it is fixed by them if sigma 1 of A equals sigma 2 of A equals sigma 3 of A and all the way up to sigma n of A. That means the image of A under all of these is equal, is the same. Okay, so this, and moreover, and this is a simple lemma. So you take the collection of all elements fixed by them, that forms a subfield of the subset consisting of subfield of K, the subset consisting of elements of K that are fixed by sigma 1 through sigma n is a field, is a subfield of K. Okay, namely, more precisely, so let's take F to be the set of all elements in K which have the property that sigma 1 of A equals sigma 2 of A equals sigma 3 of A and so on all the way up to sigma n of A is a subfield. Okay, and the proof is an easy exercise for you. I won't say much more than the following. So if you have two elements in the set F, how do you verify that F is a field? If you are given two elements, you want to show that product is there, their sum is there, if something is there, its inverse is there, identity element is there for both addition and multiplication. So all those are easy. So basically you take two elements, I'll just do one of them and you can do the others. What is sigma 1 of A plus B? That is because sigma 1 is a homomorphism, that is same as sigma 1 of A plus sigma 1 of B. But this is true for any I in fact. Sigma I of A plus B is equal to sigma I of A plus sigma I of B. But then because A and B are in the fixed set, sigma I of A is same as sigma J of A, sigma of I of B is same as sigma J of B, which is same as sigma J of A plus B. Okay, so this you use this idea to show that F is a subfield, and the important definition for us is F is called the fixed field of sigma 1 through sigma n. So if you are given any collection of homomorphisms from F to L, the fixed field is the collection of elements which have the same image under all of the given homomorphisms. Okay, and notation, instead of writing fixed field of this, we write K power this. So fixed field is K power that set, or K power S, which is more convenient, where S is this set. Okay, so these are the notations we follow. So now this really makes sense if you have at least two elements, right? Because if you have only one element, there is no condition. So sigma 1 of A. So if you have a single homomorphism, if n equal to 1, the fixed field is K itself. Okay, so this is called the fixed field. And the most so I'm going to do a few examples now, and before that let me just say that the most important case in which we will study this is when K equal to L. Okay, so the most important case for us, and I'll do one example where it's not in this case, but after that everything we do will be in this case. Most important case for us is when K equal to L. And in other words, we are looking at homomorphisms from K to K. So that is the most important case for us. So let me just highlight this. And when we come to examples and when we look at this special case, you will also see why we use the word fixed. Okay, so let me start with a few examples. I'm going to introduce these examples to you, and then we will come back to these examples repeatedly in the upcoming videos. So let me first take this field Q adjoined cube root of 2 and L to be the complex numbers. Okay, so here what we have is cube root of 2 is of course always when I write like this, I mean a real cube root of 2. The other two are complex, right? And other two are given by omega times cube root of 2 and omega square times cube root of 2. So omega for us represents a primitive third root of unity. Okay, so now what are homomorphisms from K to L? So the most important thing that I did in an earlier video, most important feature of field homomorphisms that I'll recall now is that if sigma is a field homomorphism from K to L, then sigma of cube root of 2 must be either cube root of 2 or cube root of 2 omega or cube root of 2 omega square. And the reason for this is sigma of cube root of 2 has the same irreducible polynomial over Q as cube root of 2, which is, remember, the cube root of 2 has irreducible polynomial x cube minus 2. So image of cube root of 2 under any field homomorphism, because any field homomorphism must fix Q, that is the underlying property that we are using. So image of cube root of 2 must be another root of x cube minus 2, and we know that there are only three roots: cube root of 2, cube root of 2 times omega, cube root of 2 times omega square. So choosing each one, we get three homomorphisms. Another important feature which I'm going to recall in this example, but we are going to use all these things repeatedly in all the future examples and future videos. But in the first example, I wanted to spell it out in more detail. So to give a field homomorphism from K, which is cube root of Q adjoint cube root of 2, to C, which is L, we only need to specify the image of, see, once you specify the image of cube root of 2, then the fact that it is a field homomorphism determines every other image. This is because 1 comma cube root of 2 comma cube root of 2 square is a basis of Q adjoint cube root of 2 as a Q vector space. So I'm giving you the reasons. So any element of Q adjoint cube root of 2 can be written as a rational number plus another rational number times cube root of 2 plus another rational number times cube root of 2 whole square. Now that rational number must go to itself. So if you have a plus b cube root of 2 plus c cube root of 2 whole square, where can it go under sigma? A has to go to A because any field homomorphism of an extension of Q must fix Q. B cube root of 2 must go to B times cube root of 2 because sigma of B times cube root of 2 is sigma of B times sigma of cube root of 2, but sigma of B is B, so this is the case. And finally the last term will go to sigma of cube root of 2 whole square because of field homomorphism property. So that means only choice is to determine the image of cube root of 2, and as I recalled earlier, and the only possibilities for the image of cube root of 2 are these three. So we have only three possible homomorphisms, right, from K to L, and they are 1. I'll denote it by 1, though it's a bit confusing, but 1 of any element is itself. So basically I send cube root of 2 to cube root of 2. So remember, the image of cube root of 2 determines the homomorphism, and in this first one I send it to itself. I call it 1. Second one I'll call it sigma 1, and here I send cube root of 2 to cube root of 2 omega. That's another possibility, and sigma 2 will be cube root of 2 going to the third possibility. Okay, so now I will leave this mostly as an exercise for you. If you take, so let us denote S by these three elements. S is the three element set, 1 sigma, sigma 1, sigma 2. Ks is actually Q. If you take an element of K that is fixed by all of them, that is fixed by S, meaning it must, so maybe I'll just spell it out once. It is all alpha in K such that alpha equals sigma 1 of alpha equals sigma 2 of alpha. Because alpha is the image of 1, so I will not write it as 1 of alpha, I will just write it as alpha. So if you take an arbitrary element alpha which is of this kind, right, it goes to A plus B cube root of 2 omega plus C, under sigma 1 it goes to B cube root of 2 omega plus C times cube root of 2 omega whole square. Okay, under sigma 2 it will go to something else, you can write it down, and if these are equal you conclude that it must be that B and C are 0, so that means it is a rational number. So this is the exercise. Okay, so I won't write it down because this is a good exercise for you to familiarize yourself with the notion. So in fact the same is true if you take at least two elements of this. So if you take this or this or so sigma 1 or sigma 2, they are all Q. Okay, so this is the exercise for you. So if you take any two elements of S, the fixed field is Q. Of course, if you take one element, for trivial reasons the fixed field will be K, but otherwise it will be Q. Okay, so now the remaining examples will be the cover the case we are mainly interested in. Okay, so what are these remaining examples? So I hope this is clear. This first example, the last part, I am leaving that as an easy exercise, and if needed we can discuss this in a problem session later on, or you can ask questions in problem session about it, but this is a trivial exercise. So the main case that we are interested in is when K equal to L and all homomorphisms are from K to K. So I'm going to just use, I'll not use the letter L, I'll just call it K. So this is the main case that we are interested in. So here we are, if you look at in the previous example, when K is cube root of Q adjoint cube root of 2, if you want to the target space to be also K, then these are not going to be available for us. Okay, so if we take K to be Q adjoint cube root of 2, there is only one homomorphism from K to K, namely the identity map. That is because, again, just to repeat what I said earlier, to determine a map from K, you need to determine the image of cube root of 2. That's all. Everything else is determined automatically. Once you determine the image of cube root of 2, everything else is determined automatically. And what are the possible images of cube root of 2? They are cube root of 2, comma, cube root of omega, comma, cube root of 2, omega square. But K contains only cube root of 2 because K is in Q. K is in R, whereas cube root of 2 omega is not in R. So there is only one map. So that restricts the possible homomorphisms. So now the second example that I want to study, where there is actually interesting homomorphisms from K to K, is this field Q adjoint I comma root 2. I is of course complex square root of minus 1 always. So what are the homomorphisms? Here I claim there are 4 homomorphisms. There are 4 homomorphisms. What are they? Remember, again, because I recalled this earlier, I won't say this again. I won't write it again. Image of I has to be either I or minus I, because those are the only roots of the irreducible polynomial of I, which is x square plus 1. Similarly, image of root 2 has to be either root 2 or minus root 2, because those are the only roots of x square minus 2. So there are 4 homomorphisms basically by taking all the possible images. Okay, and one more fact is, to determine a homomorphism from K to K, all you need to do is determine the image of I and root 2. And a basis of K over Q is given by 1 comma I comma root 2 comma I times root 2. So every element of K can be written uniquely as a rational linear combination of 1 I root 2 I root 2. So if you take that, if you determine the image of I comma root 2, image of I comma root I times root 2 is automatically determined. So every image will be determined. So the 4 homomorphisms will be 1, which sends I to I, root 2 to root 2, which is 1 will always be used to denote the identity map. Sigma will be I going to, sigma 1 will be I going to minus I, root 2 going to root 2. Sigma 2 will be I going to I, root 2 will be minus root 2, root 2 goes to minus root 2. Sigma 3 will be I goes to minus I, root 2 goes to minus root 2. Right? So the I has 2 possibilities, root 2 has 2 possibilities. So you have 2 times 2 possibilities for all of them together. So there are 4 functions like this. And I am going to use G for all of them. And it is no accident that I use the letter G as opposed to the letter S, because G is a group. This is an important point. G is a group. So the case in which we are going to be mainly interested in, the case K equal to L, in that case the homomorphisms form a group under composition. Okay, so here 1 is the identity element, sigma 1, sigma 2 are, and the point is sigma 1, sigma 2 is equal to sigma 3. So this is something you should check. Okay, so the composition of sigma 1, sigma 2, for example, what is sigma 1 compose sigma 2 of I? This is sigma 1 of sigma 2 I, which is I. And what is sigma 1 of I? Which is minus I, which is exactly sigma 3 of I. Similarly, sigma 1 composes sigma 2 of root 2, will be sigma 1 of root 2, which is root 2, and sigma 2 of root 2, which is minus root 2, and sigma 1 of minus root 2 will be minus root 2, because sigma 1 of root 2 is root 2, and this is sigma 3 of root 2. Okay, so I have actually checked this. So this is a group. So this is getting to the crux of Galois theory. Okay, so we will analyze this more later, and I will formally state this as a lemma in a future video. But now let's come back to the fixed fields. What is the fixed field? I claim that fixed field is Q. Okay, so this is something I'll allow you to do on your own, but just maybe I'll start the process. So here we can use more analysis here. So for example, it is a subfield between K and Q. So remember, K to Q is a degree 4 extension. So it sits inside between these two. So you take an arbitrary element of K. It is going to be of this form. Okay, where does it go under sigma 1? Where does it go under sigma 1? It goes, so that is right here. Under sigma 1 it will go to A and B, C are rational numbers, of course. C, D are rational numbers. So under sigma 1 this will go to A plus, or because I goes to minus I, it will go to A minus Bi plus C root 2. And I times root 2 will go to minus I times root 2. So this is minus d I root 2. Similarly, where does it go under sigma 2? It will go to A plus Bi minus C root 2, and I root 2 again will go to minus I root 2. So this is minus d root 2. And finally, where does it go under sigma 3? Sigma 3 sends I to minus I, root 2 to minus root 2, I times root 2 to I times root 2, right, because that is sigma 3 of I times sigma 3 of root 2, which is minus I times minus root 2. So this will go to A minus Bi minus C root 2 plus Di root 2. And Kg is all elements alpha in K, such that sigma 1 of alpha equals sigma 2 of alpha equals sigma 3 of alpha equals alpha. So all of these are equal to alpha, which is this, right? So now, using the fact that this is a basis, right, 1 I root 2, you can immediately see that, for example, comparing these two you conclude that B equals minus B, right? That means B equal to 0. And comparing these two again, we get C equal to 0. Whereas you compare these two, you get D equal to 0. So that means B, C, D are 0. That means alpha equals A, which is in Q. Okay. So simple statement. So the fixed field is K power G. On the other hand, what is the fixed field of 1 comma sigma 1? And I will let you do this. This is actually equal to, what does sigma 1 fix? Sigma 1 fixes root 2 and it does not fix minus I. So this is root 2. K power 1 comma sigma 2 will be Q adjoint I, because sigma 2 fixes I, does not fix root 2. So this requires proof. And finally, if you take K power 1 comma sigma 3, what you get is actually I adjoint, Q adjoint I times root 2. So exactly the same kind of analysis. You take an arbitrary element, express it in terms of basis, and use these conditions. Okay. So these are good exercise for you to familiarize yourself with the notion of fixed fields. Okay. So this is the fixed, these are the various fixed fields. On the other hand, you can also look at things like this. This again I claim you get Q. Similarly, if you take Yeah, so let me just stop here. So this is another exercise for you. These are all exercises. And these are very hands-on, easy to verify, just using the basis description like this. Okay, so let me quickly do a third example, which is going to be a very important example again for us later on. Let's take k to be f power f pr. So fix a prime p and a positive integer r. Positive integer r, and this is the finite field. There is only one finite field of order p power r up to isomorphism. So this is denoted by this, and of course this sits above its prime field, which is finite field of order p. Okay, now I am going to consider this particular field homomorphism from k to k. So sigma of alpha is equal to alpha power p for every alpha. So now this, in general, this taking powers is not a homomorphism, but for characteristic p field it is a homomorphism. Show that sigma is a field homomorphism. Okay, you have to show for addition. So sigma of alpha plus beta will be alpha plus beta power p, because sigma sends everything to its pth power. So this is alpha power p plus p choose 1 alpha p minus 1 beta plus p choose 2 alpha p minus 2 beta square and p alpha beta power p minus 1 plus beta power p. But because these are all going to be divisible by p, these coefficients, these are all 0 in k. So this is just alpha power p plus beta power. So this is a standard statement, and the other things are trivial. So this is the main thing to check for homomorphism. Okay, so this is a very important field homomorphism for the fields of characteristic p. Sigma is called a Frobenius homomorphism. Okay, so this is called Frobenius homomorphism, and it is a homomorphism is the exercise for you. Now sigma square. Okay, so this exercise I want to give now is the following. So now an exercise for you. I will do this in a problem session later on. So sigma square, sigma cubed up to sigma r minus 1 are all homomorphisms from k to k, and they are distinct. Further, sigma power r is 1. Okay, so basically when we talk about the Galois group of field extensions in the next video or a later video, sigma belongs to it and sigma has order r. Okay, so in later language so the exercise amounts to saying that order of sigma is r. Okay, so basically I am taking G to be 1 sigma square up to sigma r minus 1. So now the statement, this is also an exercise so I wanted to record this in this video so that we understand the various types of examples we study, but these are all going to take time to prove this. So exercise, this is one. Show that second exercise is f power p. So this is one inclusion is clear. So you have k, which is fp power r, kg and fp. Okay, so this part is clear. So easy exercise, maybe I should call it this 3. 2 is fp is contained in kg. This is easy. Okay, this is because if A belongs to Fp, we know that A power P is A. This is a feature of a finite field of order P. So that means sigma of A is A. Okay, so Fp is certainly in kg. So the exercise is to show that kg is equal to Fp. Okay, this we will do after we prove a few theorems. Okay, so let me emphasize that here. So you can try to do this by elementary methods, but we will do this. I wanted to mention all these things to motivate the kind of theorems I will prove later. We will do this after proving some theorems. Okay, so let me stop this video here. In this video we have defined what a fixed field is for an arbitrary collection of field homomorphisms, and I gave one simple example in general, but then I essentially said that the only or the most important case in which we are interested in is when the field is same on both sides k, and we are interested in maps on k to k. And I gave you a couple of examples. So let me end this video with two exercises which actually you can do without my help. These are exercises to, so the first exercise is, okay, if you have K over F is an algebraic extension. Okay, actually one of the exercises is already done. So it is only one exercise, but I will recall it for you. So K over F is an algebraic extension. Sigma from K to K is an F homomorphism. Then sigma of K is equal to K. So that is sigma is surjective, and sigma is an isomorphism in fact. Okay, this was covered in the previous problem session. So on the other hand, the other important example is if you have K to L, any, so S is a set of homomorphisms. Okay, let me stick to our main case, K to K, and G is, or S is a set of, so G is a set of homomorphisms from K to K. So K is a field. Then K power G contains the fixed field. Sorry, contains the prime field. Remember, prime field is the smallest field that K contains. It's either Q in characteristic 0 or Fp in characteristic P. So I claim that Kg contains the prime field. This is fairly easy to check. And this is a good exercise, so I won't say anything more. So prime field is always contained in the fixed field. So you have K, Kg, and whatever its prime field is. So Kg is always in between the prime field and K. Okay, so let me stop this video here, and in the next video we are going to continue the study of fixed fields. Thank you.